All right. So I'm gonna, before I move the slides, let me create a new slide here. And you know what I want to do? I'm gonna actually do what we did before. So I'm gonna say CPU here. I'm gonna have the RAM, which is gonna be kind of like a matrix. And this one's gonna be, let me do that. Let me say this. Let me make this, few rows here. And let me make this 8. And we did say that the CPU is connected to the RAM through buses. And the two buses that we talked about are called the data bus and the address bus. So we said we have the address bus, which is unidirectional. And this goes from the CPU to the RAM. And this one sends essentially the address of the first byte that we want to, in most cases, fetch, kind of the first byte of the 4 bytes that we want to fetch. And the data bus is going to be bidirectional, and it's going to move data essentially meaning kind of bits and bytes, back and forth between the CPU and the RAM. So this is the address bus, and this is the data bus. All right. Now let me make sure that I have the chat window open here in case you have any questions. Okay. So let me write a few notes here. So when we first of all, when we bring something from the RAM to the CPU, this is called load. This is extremely important, actually, and I want you to not forget that. So let me make this smaller here. So when we bring something from the RAM to the CPU, this is called loading. Now, when we bring something, or when we send something from the CPU to the RAM, this is called storing or store. So when we say store, we're saying kind of store in the RAM. And when we say load, we're saying load from the RAM. So we're not kind of loading from the CPU, or we're not storing in the CPU. Storing is going to mean sending data from the CPU to the RAM, and loading is going to mean sending data from the RAM to the CPU. So this is something that some students get wrong, and that's okay because it's kind of a terminology thing. But I do want you to think about it and make sure that you essentially know what each term means. So yeah. So let's talk about loading for a second. Can someone tell me why we load data? Like, let's say, like, why would we want to send data from here to here? Like, why would we want to load stuff from the RAM to the CPU? It's in long-term memory and accessible from there. Not clear enough. So why would we want to machine instructions? Okay, so that's a good example of why we would load stuff from the RAM to the CPU. So instructions, as we showed you last week, instructions live in the RAM. So we're going to have the instructions to the code, and for us to execute the code, we need to load it from the RAM to the CPU. So this is one kind of loading. But there's another kind which is loading data. So let's say, for example, we have an array. And let's say you write code in C and you have an array consisting of, let's say, 200 integers. And let's say you populated the array with values. So you looped through the array, you gave each element, a number. And right now you have an array of 200 integers, and each integer contains a value. Now, the array cannot live in the CPU. That's just impossible. It's impossible because, at least based on the limitations that I defined earlier, which is having only 32 general purpose registers, it would be impossible because each register is 4 bytes. So each register can have an integer, kind of a value of an integer, but you have 200 integers, and 200 integers cannot kind of live in 32 registers. It's just impossible. And if you don't have any kind of caching, and we're not going to talk about caching at this point. Again, we did say that we want to start with a simplified version where we have a CPU and we have a RAM. If you have 200 integers, those integers have to live in the RAM. There's no other kind of alternative. And let's say you want to do some operation. Let's say you want to, in C, in the language C, let's say you want to do something that looks like this. Int, sum is equal to my array 3 plus my array, 5. So this element of the array is not going to be in the CPU by default. I mean, by default, it's going to be in the RAM because you have 200 of those and you don't know which one you're going to use. So they're going to be in the RAM. And for you to be able to do this operation, you have to bring this element from the RAM to the CPU, and you have to bring this element from the RAM to the CPU. So you need to put it in a register. So maybe you can take this integer, which is 4 bytes, and you can put it maybe in, T0, for example. And you can bring this one from the RAM and you can put it in T1. And after you do that, only after you do that, you can say add, S0, T0, T1. So before you're able to do this instruction, you need to be able to load this one from the RAM to the CPU, and you need to be able to load this one from the RAM to the CPU. Now, there are other cases where you would load stuff from the RAM to the CPU. So it's not always about arrays, but arrays is a good first example or a good first use case or just case to think about and write code for. So there is a question, did instructions are in the RAM or in the CPU? So instructions will be in the RAM, but before they're executed, they have to be in the CPU. So they have to be kind of fetched from the RAM to the CPU, and after that, we execute them. But they do not live in the CPU at the beginning. It's just impossible because the CPU does not have space. The CPU has very small space. In our case, it's only 32 registers, but even in the real case, in the real world, we don't have a lot of space in the CPU. So we have to put things in the RAM. And if the CPU wants to execute instructions, it would have to fetch those from the RAM to the CPU. So instructions live in the RAM, but of course, before they get executed, they have to live in the CPU. So they have to be kind of fetched. And we don't fetch a lot of them. We fetch just, one instruction at a time for now. It doesn't have to be always one instruction at a time. Again, different CPUs may have different kind of intricacies, but for our simplified version, we have to fetch one instruction at a time. So there's a term called cache, and you may have heard of it because there's like software cache that happens, when you the caching exists all over all of our computers, whether it's in the software and the hardware, and caching is one big idea of computer architecture. So we talked about things happening at the same time, things running in parallel. That's one big idea. Another big idea is caching. And once we introduce cache, a lot of the things that I mentioned will probably change slightly. So right now, we're assuming that we have a cache-less CPU, a CPU that doesn't have any cache. In that case, we would kind of fetch one instruction at a time. But as you would kind of imagine, maybe if we had cache, maybe we can fetch multiple instructions, get them closer to the CPU, and still execute one at a time, but at least we don't have to go to the RAM every single time. So we can talk about that later. But for now, again, we don't have cache. We would have to fetch one instruction at a time. So now when we fetch this data point, this is not fetching instruction. This is loading data points, loading data. So for us to add this to that, we're actually loading the 4 bytes that contain the value of this. And here we're loading the 4 bytes that contain the value of this. And then we're adding this. So we're not really fetching instructions, we're loading data, or fetching data if you want. Although I rather that we use fetch for instructions and load for data. So we need to be able to learn how to do that. So this is kind of important. And we're going to do that in the next slide. So we're going to talk about instructions that will actually bring data from the RAM to the CPU. All right. So let's talk about that. So here's a piece of code that that I have, just kind of a sample code in C. And this first one is gonna allocate 400 bytes in the RAM because this is 100 integers. Each integer is 4 bytes. So that's gonna allocate 400 bytes. And here I'm gonna add the value of h, which in this case I'm gonna assume, well, I should tell you that it's somewhere, right? So I'm gonna say assume, let me copy this and paste it. So I'm going to say assume that h is maybe, let's say, for example, is 0, and assume that the address of the of the array is going to be S3. So this is kind of important here, but it might be, that's a lot of information. So let's do it slowly, and let's maybe use this to demonstrate what's really happening here. And if you have any questions, please ask me. So I'm going to change this one. I'm going to make it 4. So I'm going to say my array, or let's say 5. So it's only 5 integers. So that means this is one integer, 2, 3, 4, 5. So this is my array. Let me change. Are we good with that? Let me pause here and get a thumbs up and thumbs down. Okay, that's good. So this one is going to be A0. I mean, this one contains the first element, which is really A0. And this is A1. And this is, and let me get rid of actually all of those here. And this one is A2. And this one's A3. And this one is A4. So what's going to happen here, let me change the font here, is that because I'm going to add h, which is already stored in S0, to A3, I need to bring A3 from the RAM to the CPU. I have to do that. I cannot, it's impossible for me to add the content of A3 to S0 without bringing A3 from the RAM to the CPU. I just cannot do that. The only way to be able to add things, is to put them in registers. So what I'd like to do is I'd like to bring A3 from the RAM to the CPU. And this instruction is a load. instruction, right? Because I did say loading is bringing something from the RAM to the CPU. Now there's an instruction called load word, LW. And do you guys remember what a word is? We did talk about that last week. A word is 4 bytes. In this MIPS 32, the word is going to be 4 bytes. So when I load a word, that means I'm loading 4 bytes from the RAM to the CPU. And of course, the 4 bytes that I want to load are here. Now, because I'm introducing a new instruction here, let me show you how that instruction looks like. This instruction looks like this: LW register, comma, register, and let me do A, B here. That's better. Let's say register A, register B, and there's an immediate here. Actually, believe it or not, I need to actually verify that. I haven't, again, it's been a while since, yeah, I kind of swapped some things here. So it would be, let me resume. So there's an immediate, and then there's a register here. Register B. So this is the syntax. Okay, so I need to give you the syntax, and then I need to give you how that works. So the way this works is we're going to get the immediate. So get the immediate, or let's say add the immediate to the content of register B, and this will be the address of the first byte that will, let me move things around here. Okay, this will be the first byte, let me say, out of the 4 bytes, or let's say word, also known as word, that I'll be loading into, guess what, register A. I know this is kind of a lot of information here, but that's okay. We're gonna explain it slowly. It's actually not that complicated. None of that stuff is very complicated. It can be complicated if you're gonna rush through it. I mean, anything can be complicated if you want it to be, but if you're taking things kind of slowly, and if you're trying to understand every step of the way, hopefully things will not be complicated. All right, so this is the syntax. This is important, right? So we know the syntax. And what this will do is it'll add the immediate. So this immediate is going to be a number like 20 or negative 20 or 500. We're going to add the immediate to the content of register B. So register B is going to be something like T0 or S1 or S2. It's going to be a register. We're going to get the content of that register. We're going to add the immediate to it. We're going to end up with a number. This number is going to be the address of the first byte out of the 4 bytes, aka word, that I'll be loading from the RAM to the CPU. Let me pause here. I want to pause, make sure that you understood kind of what I said. If you haven't seen examples, I haven't shown you any kind of examples, but still, let me mute this. Without seeing any examples, you should be able to understand this, to understand what I'm saying here. So there's going to be a number here, there's going to be a register here. I'm going to get this number, add it to the content of this register, end up with an address, go to that address, and 4 bytes starting at that address will be loaded into register A. All right. So it seems that you understand it. And because you do, guess what? I'm going to ask you a question. That's what happens when you tell me that you understand it. And of course, I do believe you, but I want you to think about it when I give you this question. So here's the question. I would like to do this one. So I would like to add h, which is stored in S0, to A3, which is in the RAM, right? I'd like to add these two. So the first step is for me to bring A3. That's the first step. Now, here's what we know. This is all that what we know. I'm telling you that what's in H is stored in S0. This is actually not very relevant right now because your focus should be on bringing A3 from the RAM to the CPU. You have to put it in a register. So let's kind of ignore that part. Right now, we want to load this one from the RAM to the CPU so that we can add it to something. Until you do that, you don't have anything, right? Until you take this A3 and put it in the RAM, in the CPU, you cannot do this operation. So here's this part that's actually very important. Assume that the address of A is stored in S3. So this is really called the base register. And when I say the address of A, I'm talking about the address of the first byte of the array. So here's what we know. We know that there's a register called S3 that contains the address of this byte. This is what we know. And of course, we know that we need to bring this A3. Can someone give me the instruction, the MIPS instruction? Let me go more compact here. And I'm giving you time to think as I'm doing this. So I want someone to give me the instruction. So again, this is the shape, this is the format, and this is the logic. This is the you know how the instruction works. And we know that S3 contains the address of this byte. What do I need to do here? What kind of instruction can I execute to bring those 4 bytes from the RAM to the CPU, to a register? We can put them in any register. We can put them in T0 for now. So think about that for a few seconds. Okay. All right. So Anthony gave us an answer that looks good. It looks very good because the syntax is right. That's one reason that makes it very good. And if the logic is right, then it's a great answer. So let me write the answer here, and let's kind of inspect it. Let's inspect it, make sure that what Anthony proposed is correct, hopefully. All right. So what Anthony was like thinking, of course, we have to stick to this format. So it has to be load word. And I did mention that we can put it in T0. And we know that the result is going to be in register A. So Anthony put T0 here, which is great. And then we know that S3 contains the address of this byte. And what Anthony was thinking is, I need to get to here. I need the immediate plus the content of this register to point at this byte. Why is that? Because the immediate, when we add the immediate to the content of register B, we get the address that we're gonna, fetch the 4 bytes from. So Anthony was thinking, okay, S3 is here. How many bytes do I need to add to S3 so that I can end up here so that, when I load Word, the 4 bytes that I load are going to be A3. Now, if you do the math, you will realize that Anthony did it right. So here, if you add 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if you add 12 to S3, you will indeed end up here. And this is where you want to end up. Because if you're here and you load Word, that's going to bring 4 bytes starting at this byte, and that's going to be placed in T0. And then, of course, you can use T0 to add it to H, whatever register H is using. Let me pause here and ask if anybody has any questions. Okay, all right. So it seems that it makes perfect sense, and I'm very happy about that. And I really like that you guys ask questions. I really like that you're giving answers. I like that the answers are correct, but that's not really what I like the most. I like the most that you're participating. That's really the important part. And of course, the fact that you're giving me good answers is great. Oh, all right. So let's try to let's see what we have here. It's going to be very similar, actually, very similar to what Anthony proposed. It might be identical. We might not be using T0 in the answer that I have, but it would have to be 12 here and S3 here. So let's do that. Let me see. Okay, so let's look at what I have here. In fact, I'm using T0. So this is really identical to what Anthony proposed. And this is called an offset. So this immediate is called an offset because that's really the value that you're going to add to S3. It's like you're going to offset S3 by this amount. And once we have A3 in a register, in this case it's T0, you can simply add it to the register that contains the value H. In this case, I'm using S2, but really, because I told you S0, let me just say S2 here. Oops, yeah. So if S2 is used for H, then of course I will first load A3 into a register, and then I can add that to S2 and put it in S1. And again, here I'm using S1 for G. I should tell you, of course, that I should tell you for H, I'm going to use S2, and for G, let's use, S1. Was it S1? Yeah, S1. And that way, your answer will be exactly that. Okay. Any questions before we go to a new instruction? Okay, no questions. So now we're going to talk about the other instruction that goes to the RAM. And this one is called store word. And remember, store means take some data from the CPU and put it in the RAM. You're storing in the RAM. So let me actually copy this one and paste it. And I'm going to change a few things. So let me actually get rid of this. Let me do another example. Let's say my array 2 is going to be equal to, maybe 200. Okay. Now, or let me say A plus 200. So in this case, or even 200, it's going to be really the same. We would have to store word either way. Why do we have to store word? Because here I'm changing the array. And when you're changing the array, at least for this course, you want to assume that this means changing the array in the RAM, because the array elements, again, they're usually kind of more than the space that we have in the CPU, because in the CPU we only have a limited number of registers. Because of that, whenever we change the array, even if I don't tell you that, we want to assume that we're going to have to change it in the RAM. So you cannot say, I'm going to be using the register S4 for this element of the array. We can't do that. If you're changing an element of an array, that means you have to actually change it in the RAM. So the instruction looks like this: store word, register A, immediate register B. So it actually looks very similar to the load word, except that we have an SW. And I think what I'm going to say is something that some of you may guess. So here's what this instruction means, the store word. It's going to mean add the immediate to the content of register B. So this one stays the same. And this will be the address of the first byte out of the 4 bytes. All of that actually is going to stay the same, that I'll be changing. So again, in a store word, you're taking data from the CPU to the RAM. So you're not loading 4 bytes from the RAM to the CPU. You're actually changing the content of 4 bytes in the RAM. So I'm still going to add the immediate to the register that's here, and that will be the address of the first byte out of the 4 bytes that I will be changing by assigning the value of register A. I'm sure there's probably a better way of wording it, but essentially what's happening here is once I calculate the address by adding the immediate plus the register B, I'm going to take whatever is in register A, and in this case, let's simplify it. I'm going to take whatever is in register A, which hopefully should be 200, and that's what's going to go to the RAM, and that's what's going to replace the 4 bytes starting at the byte that has the address that we calculated by adding these two values. Okay, do you have any questions before I ask you a question? I can pause here if you want to think about it for a minute. It's kind of similar. I'm going to add the immediate to the content of register B, but instead of going to that address and bringing 4 bytes to this register, instead I'm going to take the content of this register and I'm going to change the 4 bytes at that address. Let me pause here and see if you have any questions. Okay, no questions. So let me ask you another question here, and we're gonna hopefully be able to answer the question together. But I do want to say, just to kind of remind you, the address of the array or first byte of the array is stored. You see, I'm not going to say stored, is in S3. Just kind of a quick reminder. We talked about that actually, and I think you do remember, but just kind of a reminder. So we have a register called S3 that contains essentially the address of this one. And what I want to do is actually this. Let me just do this. Can someone tell me what the code should be? And it could be multiple instructions to do this. Think about that. So I'd like to put 200 here in these 4 bytes. How can I do it based on kind of what we learned about, all of the stuff, all of the instructions that we covered? Okay, so Anthony, so Anthony's saying we should put 200 in a register. And this is really, let me paste what Anthony suggested, this one. Now, of course, um, we should probably use 0 here, as we said earlier. It's better to use 0 here. So I'm going to put 200 in T0. And then Anthony was saying we can actually do this. Oh, I don't know why I did this. Yeah. So let me move things. Okay. So this is what was proposed. Let me actually, maybe what I should do is just make the font a little bit smaller. Yeah, that way we don't have to be crammed. Yeah. So we put 200 in T0, and we take the 200, which is stored in T0, and we send it to the address that happens to be this plus S3. So S3 is going to be here. We add 8 to it. 1, 2, 3, 4, 5, 6, 7, 8. We end up here. And 4 bytes starting at this address are going to be replaced with the value of T0, which is 200. And that's exactly what we want. So this is the correct answer. Now, one thing that you notice here is that the 8 was actually not very hard to get or calculate, and it's because it's really the index multiplied by 4, because each element is 4 bytes. It's really the index, which is 2 multiplied by 4, and before it was 12, which was really the index 3 multiplied by 4. So it's actually, you don't have to do advanced math to kind of come up with this number. But this is good. This is the correct answer. Anybody has any questions about this? This is the correct answer. And I think this is a good place to stop if you don't have any questions. Let me pause here. Give me thumbs up if you don't have any questions. Okay. All right. So I'm going to stop the recording here, and I'm going to post the 3 videos tonight, and I'm going to also post the slides for those videos and the videos that we covered last week. Again, we're going to have a quiz tomorrow as usual. So let me stop the recording, and then I can help the students that need help with the simulator. Let me stop recording.